Hi, folks. Welcome to sixth lecture in chapter number 6. Altogether, 23rd lecture. And in the last lecture, we were talking about the partial breakdown phenomenon, which is very, very important in case of solid dielectrics. In gaseous dielectrics, it was not that crucial because it doesn't cause any uh, permanent damage. The damage caused is just a minute. The damage caused in gaseous dielectrics, it is replaceable. I mean, the gas is replaceable, but it is crucial in case of enclosed chamber gas apparatus. However, in case of solid dielectrics, wherever they may be, if the partial breakdown phenomenon takes place, that can be very injurious to the whole system. So that is why we have been discussing in so much detail about the partial breakdown phenomenon in gaseous, in solid dielectrics. We learned you can have uh, two types of partial breakdown in solid dielectrics. One, QI, the impulse discharge or impulse partial breakdown, and the QS is the sum total or the cumulative partial breakdown phenomenon. Because the partial breakdown would begin when you increase the voltage at a particular weak point in the solid dielectric. And that you can also say very easily that is the most crucial point where partial breakdown of maximum intensity takes place. So that uh, partial breakdown is called to be QI, the impulse breakdown. When you increase the voltage, you can see here we derived an equation also about the average discharge current taking place at several partial breakdown locations, which are given Q1, Q2, Q3, etc. Sum total. And here you see the oscillograms, two oscillograms. I've brought it for you extra. The top one, as you see, that while increasing the voltage, you see in the middle the current impulse is traceable here in this oscillogram, in the upper one. And that is taking place while increasing the voltage at the weakest point, or you can say the location where partial breakdown of highest intensity of discharge current takes place. So that is the inception of partial breakdown in an apparatus. But there may be not just one location where the partial breakdown takes place. There may be n number of locations. So this highest will remain the one where maximum intensity partial breakdown displacement current is measured. And when you increase the voltage further, the lower curve here, lower oscillogram you can see here. Now, partial breakdown activity spreads to number of locations, and at each one, some discharge current will be displaced because of the breakdown. So the lower oscillogram shows large number of partial breakdown activity or at higher voltage. So this is how you can measure with the help of partial breakdown detector, PV detector, available by many organization, many measuring instrument, uh, and you can analyze the partial breakdown activity, which is very crucial in case of solid dielectrics because it causes an irreversible damage, unlike in case of gaseous and also in liquid dielectrics. So we'll continue here a little bit more about the partial breakdown activity. Just a minute. Oh, yeah. Uh, the partial breakdown phenomenon in the also takes place. We did talk about it on the surface of solid dielectrics and also liquid dielectrics. So when we try to learn about that, the surface discharge, also known as tracking phenomenon. Tracking phenomenon is very untidy phenomenon. It is not desirable phenomenon at all. Even otherwise, partial breakdown is not desirable. But tracking is a very untidy and annoying phenomenon. Why does it take place? Uh, the surface discharge are, is caused when an interruption in the flow of pre-page current across the surface of a dielectric takes place. We learned that the surface resistance is all of any object, uh, material, is always lower than the volume resistance. So what happens when you apply voltage across a solid dielectric, there will be a tendency for current to flow over the surface also, proportionately to the difference in the surface resistance and the volume resistance. So the surface, the propagation of the current on the surface of a dielectric, and there may be, as we know, the whole phenomenon takes place not in uniform field. There may be a tangential field component at the location which exceeds the electric strength of the medium. The surface of the solid dielectric, it may be there may be air on it, or there may be oil, as in the case of transformers. On the surface of the transformer, on the surface of the solid dielectric in transformer, it is oil. And otherwise, when solid dielectric is used in atmospheric air, it is air. So actually, the surface discharge or surface breakdown or tracking takes place on the surface of solid and liquid with gaseous dielectrics, or on the surface of the solid dielectric where liquid is present instead of gaseous dielectrics. So, and when the tangential field intensity, um, which increases locally the electric field intensity, and that field intensity is enhanced several times, can be estimated theoretically also. And when that electric field intensity on the surface of the solid dielectric is above the medium there, that is air or oil, there will be a local breakdown phenomenon taking place on the surface of the solid. So surface discharge uh, or tracking is also a partial breakdown phenomenon. And the scientists, Parr and Scaris, brick, scarce brick, gave an theoretically tried to describe the surface breakdown phenomenon as the ratio of Tc by uh, Tm. Yeah, Tc by Tm as I put here. So Tc is the dissociation energy of all the bonds which on breaking produce free carbon. That is the is energy, so it is kilocalorie per mole unit. So this is a dissociation energy of all the bonds which on breaking produces free carbon, and divided by Tm, the total bond energy of the molecules, again in the same unit, kilo kcl per mole. What happens that uh, uh, I mean that you can say this ratio is given in terms of chemical bond energy, which depends upon a material to have tendency to track. A particular material will have tendency to track depending upon the chemical bond energy and the ratio given there. And uh, it has a tendency to track depending upon the proportion of the bond which produces free carbon. And the mm, chemical decomposition, free carbon is produced, that means there is chemical decomposition taking place on the surface of the dielectric, and that is a property of the dielectric. So that is chemical decomposition of the molecules due to, why should a chemical decomposition of the molecule take place? It takes place because of very high temperature acquired uh, by the solid dielectric. It's a property of the solid dielectric. It takes place in on the surface when air is present or oil is present, but it's a property of the solid dielectric. So when this bond is, I mean, free carbon is produced because of very high temperature rise on the surface. And why should there be a high temperature rise on the surface? It is because of the surface current, which is interrupted to flow on the surface. That is again property of the dielectric. When it is interrupted to flow over the surface and it requires a magnitude of current, temperature rise takes place on the surface, and that causes free carbon to be produced. And that was given by this ratio, par and scarce brick. And interestingly, the smaller is the ratio of Tc by Tm, less likelihood to track would be the property of the dielectric. That means when the ratio Tc by Tm is very small, there is less likelihood of the material to track or the surface breakdown to take place on that particular material. So it is a property of the material. As I said, if you want to experiment one day in your high voltage lab, you just take simple window glass, which is a cheap window glass, and put an electrode on the top, and on the bottom you put another electrode. The top one you apply the voltage, on the bottom one you just ground it, and you may increase the voltage to a few kilovolts, and you can see the surface breakdown taking place on the glass uh, sheet or glass plate, you can say. So the simple window glass has a very high tendency to track. That is why it is not used for insulation purpose in electrical engineering. You would always try to take a solid dielectric which has least tendency to track. Because as I said, otherwise the tracking would take place all its life and that is not desirable. So there are specifications to test the tracking tendency, and then only you select a particular solid dielectric for a particular application. So as you see here in this figure, uh, uh, figure 18 with me here, this is the development of positive streamer along the press board surface in oil. As I said, it could take place on the surface of the solid dielectric in oil or in air. So the upper one is a schematic shown there. And of course, the partial breakdown phenomenon, you learned right from the beginning that it takes place at extremely non-uniform field configurations. So needle is taken as high voltage electrode at the potential is applied at the tip of the surface of the dielectric, so at the surface of the solid dielectric, and on the right is the ground electrode. So the surface breakdown phenomenon takes place where begins where the Emax exists at the tip of the needle electrode, and the lower is the actual track observed on the press board surface. That is actual, you can say, photograph converted into this kind of a sketch, but it is the actual photograph of the streamer propagating from the tip of the needle electrode towards the ground electrode. And this is very typical propagation of streamer we have learned in the past. So this is about a short description of surface breakdown phenomenon, and we showed you a picture when surface breakdown phenomenon took place on the simple glass plate, and the involvement of current is so high that the there not just streamer but even the leader channels are formed towards the opposite electrode because of the high intensity current in the breakdown channel or in the discharge channel. The intensity of current would determine whether it is streamer or the leader breakdown. We had seen the leader breakdown, which could be produced at a very low few kV only in the laboratory on the surface of the simple glass. Yeah. Uh, Now let's talk about degradation of solid dielectrics caused by partial breakdown. In fact, we have learned the treeing phenomenon in solid dielectrics. And treeing, which is a pre-breakdown degradation process due to partial breakdown. Treeing is given name only for the solid dielectrics because the partial breakdown phenomenon leaves behind a permanent conductive channels uh, which develop within the solid dielectric and damage the solid dielectric. That is, if the PB intensity is unusually high, partial breakdown in solid dielectrics is unusually high, the degradation and erosion mechanism may proceed at sufficiently fast rate. This can happen. It depends upon the weak point. It depends upon the field intensity. It depends upon so many factors that which will determine the intensity of partial breakdown taking place in solid dielectric. Then uh, uh, there are, as I think I did mention, in microvolts, in some cases, like in electrical machines, the partial breakdown phenomenon takes place continuously all throughout its life, uh, but at a below critical intensity. So it does not damage, and the apparatus lives with it. But there are conditions where it can be damaging, where there are conditions when the partial breakdown may develop the conductive channels very fast. It may not develop at all. It may develop slowly, as we learned in the development of partial breakdown. The time required for the breakdown channels to appear, to grow, and the total breakdown takes place in the previous lectures, explained by Pilling. So the uh, conductive channels in at different uh, conductive channels in different shapes and sizes are formed. Yeah, that is very interesting. That is, the treeing phenomenon may not be the same in every dielectric. That is, treeing is nothing but the formation of conductive channels within the solid dielectric. And it may not be the same pattern everywhere. I showed you one of the patterns which has been acrylic formed in acrylic block in the last lecture. So the treeing of different types are produced. Interesting type, bush type, and other types. People have given several names to the treeing phenomenon, which depends upon dielectric to dielectric and condition to condition. That means, which may also depend upon which type of voltage you are applying. When you are applying AC voltage to the solid dielectric, or DC, or an impulse voltage, different types of treeing phenomenon may grow. If you look for it, bow type and whatnot, so many scientists, the type of treeing they have observed and given a certain name, and maybe any type of it. You may come across if you are actually working with a solid dielectric and are able to develop a tree which is really looking like a tree, not a burnt out dielectric. If you do not discontinue with the application of the voltage, the whole dielectric may burn out because it causes a short circuit. So the conductive channels in different shapes and sizes are formed within the solid dielectric, known as tree phenomenon or treeing phenomenon or tree formation. The phenomenon is known as treeing process. It grows towards the opposite electrode with time, as we have learned. It may lead to complete failure of the insulating properties of the dielectric, taking different amount of time. As I said, it depends upon the magnitude of the partial breakdown. It also depends upon the material, whether the conductive channels are able to grow or not. People are trying to develop such solid materials where the conductive channels may begin but may not be able to grow up with the composite dielectric with nano dielectrics are being offing out and are being produced to make the solid dielectric treeing or tree resistant. So that is a very wide research field today. So, uh, uh, the treeing phenomenon is not uniform in every dielectric. This is the main thing you should know. Yeah, I mean, treeing resistant dielectrics are coming up. Uh, yeah, it also depends upon the field intensity configuration. I mean, very sharp uh, needle electrode, the intensity of field increases so high that the dielectric may not be able to resist that, and field phenomena may grow. And as we learned, that the treeing process normally begins at a very sharp pointed electrode, which because it forms the extremely non-uniform field due to internal partial breakdown, which takes place under extremely non-uniform field conditions only. Then the extreme field distortions at protrusions we have also learned in the longitudinal cross section of the power cable. If there is a protrusion of some conductive material within the dielectric, that forms an electrode in the dielectric with sharp electrode, and the field intensity is high there, and the whole phenomenon may begin at the tip of the protrusion, call it, in the dielectric. May also give rise to development of treeing process. Treeing may occur and develop slowly due to partial breakdown. As I said, uh, it may take place slowly and of low intensity, as in the case of microvoids. In the presence of moisture, moisture always would be conductive. So, any uh, presence of conductive material within the solid dialect is not desirable. So, in the presence of moisture, it may develop slowly, it has been found, even without any measurable quantity of PV. I mean, that is working, moisture is working as kind of a field equalization. So it may develop slowly, people have found. But ultimately, the breakdown strength would be lower if moisture presence is there in the solid dialect. However, treeing develops rapidly when very high impulse voltage is applied. When we apply very high impulse voltage, as you see here in this, we have seen once. Uh, this is epoxy resin. The earlier block, what I had showed you, the physical block also, that was in acrylic uh, in solid insulating block, and this is a epoxy resin block. So in this photograph, development of treeing process in epoxy resin used with this has been used with the permission, as I mentioned, Mr. Uh, Hickman, and this is courtesy to Hickman that he has allowed for showing it to educate you. So this uh, this has been given rise to, as you see on the top of the block, a sharp electrode, needle type electrode, is impinged on the block, and then uh, 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 then a very high impulse voltage is applied. See the treeing, what you see here is being produced by applying an impulse voltage, or rather pulse voltage. That means the duration of the voltage is in microseconds. So very short pulse of adequate, adequately high intensity of voltage or magnitude of voltage has been applied, which has given rise here this kind of a tree phenomenon. If one had applied continuously, for example, AC or DC voltage there, the development of treeing would have been entirely different. So that is what I was trying to make. The different bow type, bush type, whatnot types of treeing phenomenon are observed. So this is this, as I put it, is like an inverted tree. If you uh, if you have observed a tree without the leaves, and there is the season autumn in Europe and spring in our country in India, when the tree tree sheds out all leaves, only the branches are you can see all the branches. And the branches, when you appreciate that the branches of the tree do not intersect each other, they are spread in volume, and the branches, they are stronger at the bottom, weaker at the top. The same phenomenon, same pattern you see of the development of treeing phenomenon in the solid dialectic, and that is why it has been given the name of treeing phenomenon. Treeing process developed in solidified resin is shown in this figure. A needle electrode embedded, as I mentioned, inside the resin block produces an extremely non-uniform field at the tip of the electrode, and this gives rise to partial breakdown within the solid dielectric on applying a voltage greater than, obviously, the inception voltage, the PV inception voltage. The PV, the partial breakdown, causes formation of conductive channels due to degradation of the dielectric under heat. When the partial breakdown produces heat and the decomposition of the dielectric takes place, and it may produce gases also, and which help in propagating the conductive channel. And these channels develop in the form of tree extending towards the opposite electrode, that is towards the ground. And when you just invert this figure, this looks like a tree, and at the top, what is here, if we come to the bottom, is the stem of the tree. Yeah. We'll uh, discuss not everything today, maybe also in the next lecture, but I'll introduce you what we are going to talk in the next lecture. So long, we have not talked much about the complete breakdown in solid and liquid dynamics. Now you can imagine that in case of solids and liquids, the breakdown phenomenon is affected by large number of factors. That is the condition of the dielectric. The foreign particles presence, the foreign particles, that is the formation of voids, you can say foreign particles, presence of foreign particles, formation of voids, micro voids, or bigger voids. So there are very large number of factors which affect the breakdown phenomenon in solid and liquid dielectrics. So it is very difficult to standardize or say this is the breakdown strength of this dielectric, because the condition of the dielectric and the measurement conditions under which it has been measured would determine the breakdown strength. So there is no one value of breakdown strength in case of solids and dielectric. So the breakdown mechanism, but the breakdown mechanism is similar to those described in gaseous dielectrics. Mechanism. The phenomenon of partial breakdown takes place only in extremely non-uniform fields, we have learned, before the complete breakdown. So the partial breakdown leads to the treeing process, and the development of treeing process would determine also the breakdown strength. And because the treeing process ultimately does lead to the complete breakdown. The breakdown strength also depends strongly upon the type of voltage applied. When you apply AC voltage, DC impulse, or the lightning impulse, or switching impulse, every type of voltage, the development of partial breakdown or the propagation of the partial breakdown channel, which is leaving behind the permanent conductive path in the solid dielectrics, or also in case of liquid dielectric, are completely, the phenomenon will be observed to be completely different. The breakdown strength of these dielectrics is distinguished, therefore, into two broad categories of breakdown. That is, one is the intrinsic breakdown strength, and another one, practical breakdown strength. That means under the practical conditions when the dielectric is used, not the ideal conditions. The practical conditions may be completely different to the ideal conditions. And the ideal condition, breakdown strength, which is certainly going, should be much higher, the strength, is known as intrinsic breakdown strength. And the solid and liquids have got so high breakdown strength especially under the intrinsic condition, that is ideal conditions. Intrinsic means inherent. Under the ideal conditions, measured under the ideal conditions of the breakdown strength, which the dielectric inherent is present inherently, you can say, is known as intrinsic strength. And because it is so high, unlike in gaseous dielectrics, that is uniform field for 1 centimeter gap distance, it is not measured for 1 centimeter gap distance. Of course, it is measured in uniform fields for very, very thin films of solid dielectric, or for very small gap distance in liquid dielectrics, because the breakdown voltage required to produce the breakdown is so high that on small samples it cannot be applied if the thickness is high. Suppose 1 centimeter gap distance, the breakdown voltage required would be very, very high. So it is taken in very thin film. The measurement is done on very thin films of micrometer thickness. So that gives rise to the intrinsic strength. And also for practical strength in solids, again, it's very complicated, and it's not also very reliable because of the external factors which affect the breakdown. But in case of liquid dielectrics, some standard procedure for practical breakdown strengths have been derived, have been developed. So we'll be talking about the intrinsic strength and practical breakdown strengths of the solid and liquid dielectrics in our next meeting. So I think we can uh, stop for today, and we'll be meeting in the last lecture on solid and liquid dielectrics breakdown strength or breakdown in solid and liquid dielectrics. That is chapter 6 in our uh, uh, next last lecture. Okay.